Hey, good morning and hello there. This is attempt number 3 at this same video. Hopefully this time the entire screen is actually captured. If you go onto my YouTube channel, you can see a previous attempt at which I only had about 2/3 of the screen. So a lot of what I was talking about, it turns out, wasn't being recorded. I just need to figure out how to delete that video from YouTube. Anyway, so you guys' homework on reaction rates is what we're going to go over here. We're going to go over just parts A and B, and then you're going to take the quiz I was talking about on rate laws. So that's going to be not too hard actually. So let's delve into it. Number one, we have a reaction or experiment occurring, and they tell us a lot of interesting pieces of information. They tell us how many moles are consumed. They tell us what volume they occupied, and they tell us the time it takes for this to occur. And that time piece is a little bit harder to see here. And it says each second of reaction. So that is our time piece. And typically, when we're talking about reaction rates, we're talking about rate units. Rate is typically in molarity per time. So those are the typical units for rate. It's the change in molarity, I guess I should have said change in molarity as time occurs. So we need to figure out how the molarity has changed. We have 0.0048 moles being consumed, and then it's in 2 liters. So I have 0.0048 moles divided by 2 liters, because as we all remember, molarity equals moles per liter. So I divided the moles by the liters, and then I have to also divide by the time unit. In this case, the time unit is a second. So the rate of consumption for pH 3 is 0.0024 molarity per second. Now, that negative sign and these plus signs in a second kind of depend on how you write it. If you said the rate of consumption is, you wouldn't put the negative sign in there. But if you just said the rate of pH 3 equals, you'd have to have the negative sign to indicate that it was decreasing. It's all about kind of how you write out your answer, I guess, in that case. The other two things we're supposed to figure out is what are the rates of production of the phosphorus and the hydrogen on the product side. And this is not difficult at all. Now that we know the rate for the pH 3, we can just use the mole ratios. For every 4 pH 3s, there's going to be 1 P4. We're just using those ratios. That's what's going on right here. We have the 1/4 ratio and a 6/4 ratio to convert from pH 3 to P4 and to H2. Those two rates are both positive because we are producing those two compounds. All right, let's move on to number 2. So we have the Habra process, which is one of the most famous reactions. We'll talk about that on a different day. And we're supposed to look at the mole ratio and figure out what the rate of consumption would be. So we'd use that 2 to 3 ratio. And let's go ahead and just imagine, let's see, what is between the rate of production and the rate of... So if we had the rate was, let's say the rate was 4 molar per second for hydrogen's consumption, then we would multiply that by 2/3 to get the rate of production for ammonium. I didn't pick out very good numbers, did I? It would be 8/3 molar per second. What is that? 2 and 2.6. 2.6 molar per second. So you would apply that ratio, the ratio of hydrogen's use or consumption could be applied to determine the rate of ammonia's production. In number 3, we are told the rates of 3 compounds inside our reaction, and we don't know what the coefficients are. And the rates should tell us the coefficients if they have a common multiple. So we look at these, and I typically kind of try to just imagine they're all the same value. That didn't work. There we go. Let's cross off those first two zeros on all of them. And I have 80, 120, and 60. And 80, 120, and 60 are all divisible by the same number. They're all divisible by 40. But in reality, those two zeros are there. So I would divide them all by 0.0040, and I get my coefficients, 2, 3, and 4. Again, I look for what they were all divisible by so I can get a common factor and figure out the coefficients. And number 4, we're looking for the rate law for some elementary reactions. First of all, let's kind of look right here where it says, elementary reactions only occur in one step. That means the reactions, since those reactions only occur in one step, their coefficients are directly related to their order in the rate law. Whereas if it was a multi-step problem, the rate could be a little bit more confusing. The rate law could have a little more steps to it. But so this is going to be pretty easy. We just look at the reactant and we plug that in. We look at the reactants and we plug them in. And these are all gases. It's not too surprising that the rate is directly dependent upon those concentrations. It's pretty straightforward, doesn't take us too much work because they're elementary steps without anything silly going on. If it was anything more complicated than an elementary reaction, they would have to give us data, which is what we're going to look at on worksheet B. Alright, let's remove those comments there. There we go. So here we have a more complicated reaction. It's not an elementary reaction. That phone call brought to you by a hang-up. Person didn't even bother to wait around. Fantastic. So at number 5, we have a reaction that's drastically more complicated. It's not occurring in one step. It actually occurs in 3 steps, as we can see. And what I want to do first is I just want to skip down to part B here. Part B is all 3 of these reactions combined together. All 3 of them combined together, so you just add up the reactants, you add up all the products, and then you remove anything that both sides have in common. The things they have in common are going to be called intermediates. For instance, in reaction 1, we have this CH4 producing C4-9, and C4-9 is then used in the next step. So the thing that's being produced is immediately being used up. So it's temporarily around. And that temporary existence of one of these compounds in production and usage is called an intermediate chemical or intermediate compound. You can remove it from the total or overall equation. So it's required, it has to be produced, but you don't see it from your outside perspective. And while we're talking about intermediates, let's also talk about catalysts. Catalysts, as you know, reduce the energy level required and end up speeding up the reaction. And what a catalyst ends up doing is, so let's just imagine there's catalyst X in the first step. And catalyst X might help break these two things apart, and then it's bonded to B, and then later on, after a series of reactions, X is reproduced all by itself. It breaks free from the B later on in these reactions, and because now it's free, we would be able to remove it from the reaction. So a catalyst is kind of like an intermediate, where intermediates are produced and then removed. Catalysts are put in at the beginning and then reproduced at the end. And therefore, the catalyst doesn't get used up because you put it in the beginning, it goes through the reactions in some path, and then gets produced at the end. And so X is available for the next reaction, and the next reaction, and the next reaction, again and again. And that's how catalysts are like intermediates, but they're slightly different than intermediates because you still have them around afterwards. All right, now that we've done B and a little bit extra on C, let's go back to A, the one I skipped. You probably noticed that I skipped it. So in A, we're supposed to figure out what the rate law is based off of this proposed mechanism. And what does this mean? This proposed mechanism means that someone knows this reaction is occurring. They've got it going on in the lab. And they are suggesting that it occurs in 3 steps. There are the 3 steps. And since there's 3 steps, the proposed mechanism could be slow, fast, fast, where the first step is slower than the other 2 steps. And we talk about speed in this way. Relative slow, fast, fast is kind of weird, but usually it's a factor of 100 times different, where the one speed is 100 times faster than the slow speed. So where one thing occurs in a blink of an eye, the other takes an hour. So we don't even care about the blink of an eye because we're still waiting for that first hour to pass. So when we change anything about the slow step, it's going to have a big impact on the rate, because if you can do anything to make that hour take half as much time, that's going to be important. Now again, even if you to make it take a half the time, go from an hour to a half an hour, the blink of an eye is still a blink of an eye. So those fast steps are still so much faster than the slow steps that they wouldn't be included. So this proposal has the first reaction being the slow step. And that's the easiest scenario. By far the easiest scenario, because in the first reaction, how many reactants are there? There's only one. And so since there's only one reactant in our slow step, that's our rate. The rate is equal to the constant times whatever you do to the molarity of that compound. So if you double that compound, the rate should double. If you triple it, the rate should triple. So that's pretty easy when the first step is the slow step. Let's imagine for a second that this was fast, slow, fast. I'm sorry, I'm writing with my finger here on my touch screen. It's not the best. So we'll do this instead. Let's imagine it was fast, slow, fast. So in this second scenario that I've just created that wasn't originally asked, this second reaction is the slow reaction, right? And in order for the second reaction to occur, that first reaction must also occur. And so that first reaction is going to impact the second reaction. The slow one can't even begin to go until the fast one goes that's ahead of it. So if the second reaction was included, we would have all of the reactants from the first reaction as well as the reactants from the second reaction. So we would have both components put into the rate. And the same thing would be true for the third reaction. If we had slow as the third step, we would include all of the reactants from the first and the second step. We would not include any of the reactants that got canceled out, like that C4H9 gets canceled out. It would just be based off of those 2 reactants. Or if it was fast, fast, slow, then the C4H9 would cancel, and the C9OH2 would cancel, and so the reaction mechanism, the reaction rate, would actually just reflect those 3 reactants. And that kind of makes sense, because those are the 3 reactants we're seeing in the overall balanced equation. So if the reaction was based off of the third step, then we would expect it to include all of the reactants. Alrighty, so proposed mechanisms are all about which step is the slowest and which step is the fastest. Truly the way you would figure this out this part here out is typically in the reverse. Usually we look at data and we figure out what the rate law is, and then after we know the rate law, we would then propose which of these two combinations, or three combinations, if I had actually typed the third one, which of the combinations makes the most sense with this rate law. And obviously we need to start looking at some data. So let's move on to the next page. I'm kind of rambling here. All right, now we're homework B. So homework B, part 1, is really focused on the units. So let's talk about ways of writing units. Not everyone's favorite thing to talk about, but I'll do it anyway. Bump this up a bit. Pause. Okay, so again, let's focus on the fact that we're talking about molarity, right? Anytime we see brackets, we're talking about molarity. Molarity means moles per liter. A very common thing you're going to see in this chapter, though, is instead of writing moles per liter, they'll write moles liter to the -1, which, of course, means that that's the inverse of liters, which is the same as per liter. I'm not sure why they prefer to write to the -1 when writing per liter takes just as much physical space, but I tell you what, they are really obsessed with writing to the -1. That's my warning, right? Really obsessed with writing to moles times liters to the -1, which is code for molarity. Just pure evil sometimes, I think. But anyway, let's kind of go back and look at the answers. Number 1, what are the units for a rate? Rate is the change in molarity per change in time, right? So it's per time. So what could that mean? That could mean instead of, you could have moles, liters to the -1, and then some time unit to the -1. Days, hours, seconds. And for the rest of these answers, I've chose seconds because that's one of the more common units. It's the base unit. It is the internationally accepted unit. So I did most of them in per seconds. If we're talking about the rate constant units, the rate constant is trying to make the two sides of a reaction equal. So here is our basic rate law. We have the rate, we have a constant, we have the molarity of some substance X, and that substance X is going to be raised to some certain order or exponent. It's either going to be 0, 1, or 2, but when we plug different values in, it's going to impact the units for K. Since rate is always going to be molarity per time unit, and on the other side we have molarity to some power, as that order changes, K's units will change. So that's what we're seeing in these 4 answers, is different iterations of K dependent on what that question mark is turned into. So let's look at the first one. If it's 0 order, then we're replacing this with a 0, and anything to the 0 is 1. So there's no units when you do that. You go, whatever value to the 0 power kills all those units. And then you have molarity per second equals whatever the units for K have to be. Well, if K has to equal that, then K has to be molarity per second, because they have to be equal. The next scenario is, well, what if it's to the first order? All right, well, if it's to the first order, then we're going to have our molarity unit to the first power, and so then K has to be per second to make the two sides equal. That makes sense. And then we have, what if it's to the second order? Well, if it's the second order, things do get a little trickier, because K has to make the two sides equal, so you actually have to be dividing by molarity. That'll cancel out a molarity, and you have to be dividing by seconds. So that's why up here I have 1 over molar second for second order. And for our last question here, E, I know it says third order rate law, but really what we're talking about is maybe you have x to the second and y to the first. And so K has to deal with both of those powers. So like molarity squared times molarity, which would actually be molarity to the third. And so the K units just have to cancel out more of the molarity values to make the two sides equal. All right, number 2. Now we're finally getting into some data. Yeah. I don't know if you could hear that. That's the excitement of me rubbing my hands together because I like data. I can almost see you smiling through the screen. So we have some data here. It is a reaction between nitrogen monoxide, chlorine, and we're making NOCL, nitrogen, oxygen, and chlorine. I can't remember the name of that thing. But what we're going to look at is how changing these values is impacting the rates, right? Take the whiskers off of there. So you could pick either compound to start off with. I'm going to pick the nitrogen monoxide because it's the first column. And I'm going to pick these two data points here for nitrogen monoxide. The reason I'm picking those two data points is because the chlorine values are not changing. So I can cross off these two chlorine values because they're not currently changing. And by cross off, I mean I'm mentally crossing them off. I'm not actually going to put a big X over them on my paper. But I want to be able to compare how changing NO impacts the rate. And what I see there is that NO is doubling. It's going from 10 to 20. And the rate is going from 36 to 145. So what factor of change is that? If you pick up a calculator and do the math, you'll see that 145 over 36 is actually equal to 4. And then 2 over 1 is still 2. And so then what must be the exponent that makes the two sides equal? Or must be squared. NO must be squared. I know I say things like 145 and 36. I just end up moving the decimals so I can handle the math in my head easier when it's really 1.45 and 0.36. But anyway, so now let's move on to the chlorine. For the chlorine, I'm going to cross off these two values of NO. I see that the chlorine is doubling there, and look, the rate is doubling. That I can do that in my head. If the rate doubles as the chlorine doubles, that means chlorine is to the first order. Now that I have my rate law all figured out, I just need to solve for the constant. And we could do this by plugging any one of these values in. It looks like I chose to use the third set. I plugged in the data into the rate constant, 1.45, 0.2, 0.2, and I solved for the mathematical value. You easily get 180. How did I get those units? I did exactly what we were talking about a second ago. I have molarity per minute equals K, and then I have molarity squared times molarity to the first, and K has to make the two sides equal. So definitely K is per minute, as you can see here. It's minutes to the minus 1. And then the other thing K has to do is K has to cancel out 2 of the molarity values to make it just 1, 2 of the molarity units to make just 1 in the answer. So it ends up being 180 molarity to the negative 2, minutes to the negative 1. And there you go. I probably wouldn't be satisfied right now. I know that I did the work right, I feel good about it, but if I want to feel great about it, I easily take that K value, which does not look like that, the K value, and maybe trial 1, and I solve that and see if it equals the rate. 180 times 0.1 squared times 0.1 does equal 0.18. And I've just confirmed to myself that I did everything right. And there's nothing like finishing a question, being able to test the question, and immediately know that you're right. Let's go to the next one. Number three, we have a compound that's decomposing. It's one molecule breaking down, and we have a whole bunch of values we can kind of test. You could pick a bunch of them. I would definitely pick this value here, and then you could pick any of the other four. I do best with things being doubled, so I would probably pick this value here. All four of them are 10 to the 16th, so I'm just going to ignore that, because when you do 2 times 10 to the 16th divided by 1 times 10 to the 16th, the 10 to the 16ths cancel. So basically now I have 2 over 1 to some power, equals, and then I'm going to write those two other things. Now when you look at these values though, those exponents don't match. The top value is 10 times bigger. At 2.66 is 10 to the 4th, so it's actually 10 times bigger. So I'm going to write it as 26.6, actually making that number 10 times bigger than the way it's written, divided by 6.64. Now both of them would be 10 to the 3rd, and if they're both 10 to the 3rd, then the 10 to the 3rds cancel out, and I pick up my calculator, do some math, and guess what 26.6 over 6.64 is? You got it, 4. So we have 2 to the x equals 4. Therefore, the impact of NOCl has a squared impact or second order impact on the rate law. The sound of me undoing everything I've just done. Part B, calculate the rate constant. Mathematically, this is pretty easy. We're going to plug in one of these values and one of these values into here, right? And solve for k. Now, the numbers in these values are a little bit crazy. We have 10 to the 16th, 10 to the 4th, stuff like that. And we plug that all in. And we're going to take a 10 to the 4th and divide it by a 10 to the 16th. And the 10 to the 16th is going to be squared. So we have 10 to the 16th, and 10 to the 16th squared is like 10 to the 32nd. But we're dividing by 10 to the 32nd. So this number, while it looks weird, is the right answer. Is 6.6 times 10 to the minus 29 is the value for k when we divide the rate by knuckle squared. Units wise, units are pretty weird here. If you take a look at the units given in the data table, we have molecules per cubic centimeter, which are going to be divided by molecules per cubic centimeter squared. So a bunch of those units are going to cancel out. We end up with per seconds per molecules, and we're going to have, let's write that down, cubic centimeters. So we have per cubic centimeters divided by per cubic centimeters that are squared. And so the one cancels the other on the bottom, but then we have a reciprocal inside the reciprocal. You take the inverse of an inverse, you get it to flip back to the top, which is why in these units here, cubic centimeters is not a negative exponent. It's actually on top now in the k value. So this is the answer for k. It's k's units. And then part C, we're supposed to change molecules per cubic centimeter or centimeters per molecule into molarity units. So how do you go from molecules to moles? Use good old Avogadro right there. And then cubic centimeters are identical to milliliters. And since they're identical, I use the same ratio I would with milliliters. I said a liter is 1,000 cubic centimeters, and I was able to convert my molecules in cubic centimeters over to moles per liter. Number 4 is probably the trickiest question we have. Let's erase my little notes there from attempt number 2 to make this video. Here's why it's hard. Look at those values on iodine. Iodine is changing in all 4 data sets, and that's just mean. You don't actually have a consistent thing to look at for the OCl, which is going to make figuring the OCl out way more difficult. But we could definitely figure out the iodine's exponent pretty easily. So where are we going to do this? We could do it right here. We could cross off these OCLs mentally, and we're just comparing those two numbers. So we have 12 over 6, which is definitely 2. So we have 2 to some power. And then on the other side, for the rates, we have 7.91 over 3.95. They're both times 10 to the minus 2, so those pieces cancel. And if you do that math, you're going to get just about 2. So what is x? X would be to the first power. So that's why we have first power there for iodine, because as iodine is doubled, the rate is doubled. So if iodine is doubled, the rate is doubled. So now it's time to try to figure out what's going on with the OCl. I picked reaction 1 and reaction 2 right here. That's what's going on with this math here. Reaction 1 and reaction 4, that is. 1 and 4, I picked them because they actually have the same rates. So if I plug those rates in, if I plug the rates in as a ratio, they cancel out. So they become 1. The constants should be the same. So the constants become 1. And so what we have left was we have 1 equals, what is this? 12 over 24, 1/2. And then we have 18 over 9, which is 2 over 1, to what power? What power must x be? That must be an exponent of 1, or order of 1. That's pretty nasty, not going to lie. I don't like it, but it's doable. We have the 2 rates, plug them in, they would cancel out. K's have to be the same value, they would cancel out. We know the impact of the ICL, so we know they're both to the first order. So if these are to the first order, that doesn't really do anything mathematically other than stay as 1/2. And so the last component, which was 18 over 9, or 0.18 over 0.09, is the same as 2, and we need it to be 2 to make the whole equation equal, so x must be to the first order. That was really hard by comparison to some of the others. Now we have our initial rate that I plugged in. Oops, not that one. This initial rate that I plugged in, and I plugged in this data. They were both to the first order. Kind of looks like I'm making a weird emoji or something. But you solve for K, and K is 3.7 per minutes per molarity after you try to deal with all those different units. And then we have, what if we plug 0.15 into both spots, and we plug our K into there. We plug 0.15 into both spots and the K into there, and we can calculate the rate for a new reaction. So this one's got a lot of pieces that I like. It's got calculating the rate using an established molarity rate law. I like this one, how we've got like the doubling going on, and we look at those rates. And this one, though, I think is probably the most representative of what we're going to see in the future. And we're not going to do C yet, so we're done. Closing it down. Good luck, you all, on your test. You're definitely going to need a calculator. Your quiz. I'm sorry, I said test. I'm so sorry. I'm so sorry. I'm so sorry. Good luck on your quiz. And your homework after the quiz is to work on worksheets C and D.